Okay, so the first question is what potential difference is the work done per unit charge? So the potential difference is the work done per unit charge. Now, that is the amount of energy that is transferred to the charge carriers in the circuit. So what does that mean? It is the energy given to the electrons. Those are the charge carriers as they move around the circuit. So as a definition, which you need to remember, the potential difference is the work done per unit charge. Okay. Now, the next part is question 2, which is the difference. Potential difference is also known as voltage. So PD, if we abbreviate this, it's another word for voltage. So if when you go back to question 1, that is the same as saying voltage is the same as the amount of energy given per unit charge. Okay. Now question 3, potential difference expressed as a formula. So voltage expressed as a formula, it is the work done per unit charge, which is the work done. The word per, if you look at the definition, is the divide sign. So we'll go and write it out as the work done divided by the charge as a letter, a symbol formula. A potential difference, remember, is just another word for voltage. So we write V for voltage. Work done, we'll write W, or energy, we can write E there instead, or and then divide that by the charge. And we use the letter Q to identify charge. So as a symbol formula, the voltage, the potential difference is equal to the work done divided by the charge. Question 4, resistance. Resistance is the potential difference divided by the current. So R is the resistance in symbol form. Potential difference we said was voltage, so V, and then we use the symbol I for current. Okay, so it's the potential difference divided by the current. Question 5. Resistance is measured in ohms. Okay, so as a symbol, ohms is, it's like a hat. That's the omega symbol. It's a Greek symbol, and resistance is measured in that unit there, ohms. Question 7. So what does Ohm's law state? Ohm's law states that let's read through here. So the current through a resistor at a constant temperature is directly proportional to the potential difference across the resistor. That sounds right straight away. Let's have a look at the charge through the resistor at a constant temperature is directly proportional to potential difference, or the current through a resistor at constant temperature is proportional to the potential difference across the resistor. As you notice, we've got the words proportional and directly proportional. We're looking for the word directly proportional. So that's in these 3 statements. And we know it's the current, not the charge. So we've got the current, and they start off similar, these first and the last one for me. The current through a resistor at constant temperature is directly proportional to the potential difference across the resistor, and here it says power, so that's not right. I'm going to rub that out there. So what we're looking for, this here is what Ohm's law is. The current is directly proportional to the potential difference. Okay, that is Ohm's law. Okay, so for a constant temperature, the current, as we increase the voltage, the current will increase in direct proportion. Graphically, that looks like, I'll just put that out, sketch it out. If this was a current I and this was a voltage V, graphically that would look like a straight line going through the origin. That's what directly proportional signifies, that it passes through the line passes through the origin. Okay, so the answer here is that one there. Okay, next question 7. The current through a wire is 0.75 amps when the potential difference across it is 5 volts. So what have we been given? We've been given the current. So we've got the current of 0.75 amps. That's here. We've been given the potential difference of 5 volts. Okay, and we've been asked to calculate the resistance. Okay, so we know formula, so that's our question mark. Do we know formula that connects all three? You should remember that resistance is equal to the voltage divided by the current, and putting the values in, that will be 5 volts over 0.75 amps. And if we quickly do that on a calculator, okay, there we go. So what were the numbers? 5 divided by 0.75, 5 divided by 0.75, and that gives us 6.66 reoccurring, and that is our value there, 6.67 to do 2 decimal places. Question 9, okay, question 8, sorry. You've got the current through the bulb is 4 amps and the resistance of the wire is 30 ohms. Okay, so calculate the potential difference or the voltage. Okay, so that's our question mark. So voltage is our question mark. We have been given the current as 4 amps. The resistance we've been given as 30 ohms. Okay, and now what we need to do is we need to work out a formula that connects all three of these. And as we saw previously, the formula was resistance equals voltage over current, and we need to rearrange this formula now. So some of you use a rearranging triangle, and the R will go at the bottom, V and I here. So we want to work out the potential difference. So voltage is equal to the resistance multiplied by the current, and that gives us 30 ohms multiplied by 4 amps, and that is 120, and it's a potential difference, which is volts, so 120 volts, which is this answer here. Question 9. The resistance of a variable resistor is 3 ohms. So we've got the resistance is 3 ohms. The potential difference is 12 volts. And we want to work out the current through this variable resistor. So that's our question mark. Again, do we know formula that connects to 3? Yes. It's the same as what we've been using in the previous question. So resistance equals voltage over current. Put that again in the rearranging triangle, as we said earlier. R in the bottom left, V and I top and bottom. And if I want to work out current in this scenario, so current is equal to voltage divided by resistance. And that gives us the voltage is 12. The resistance is 3 ohms, and 12 divided by 3, that's 4, and current is measured in amps. Okay, so that's 4 amps, and that's the answer there. Now moving on to the next question, question 10. A torch bulb, when it lights, normally allows this much current. So current is equal to 0.015 amps through it, and has a potential difference of 6 volts around it. So a light bulb has a voltage of 6 volts and a current of 0.015 through it, and what we're working out is the resistance. So that is our question mark. So resistance is equal to voltage over current, as we have used in the previous questions, and that will be the voltage, which is 6 volts, over the current, which is 0.015, and let's work that out. 6 divided by 0.015, and that is 400. So the resistance is 400, and remember, resistance is measured in ohms, so 400 ohms, and that's your answer there. Okay, question 12. So we've got, question 11. A torch bulb, when it lights, normally allows a current, again with same question. We've got a current of 0.015 amps through a potential difference of 6 volts, and calculate the charge passing through the torch bulb in 1100 seconds. So we've got time given to us of 1100 seconds. Okay, so we've been asked to calculate the charge. So the charge, we use a letter Q as a symbol. We could just write charge, but I've just abbreviated it. Okay, so we've got, in this question, we want to work out charge. Do we know a formula that has charge in it? Okay, so yes, we do. There are two. We've got the potential difference is work done divided by the charge, but we also know that the charge is equal to the current multiplied by the time. Okay, so in this scenario, which formula do we use? We've got two. So the first one is the potential difference is work done divided by charge, and the second one is current multiplied by time. So let's have a look. So which one is appropriate? Do we have the voltage? Yep. Do we have the energy transferred in joules? Nope, nope, nope. So this formula we can't use. Let's see if we can use this. Do we have the current? Yes. Do we have the time? Yes. Okay, so did we need voltage in this question? Not quite. Sometimes there's a lot more information than is needed. So the current multiplied by the time is the formula we need. The current is 0.015 amps multiplied by the time 1100 seconds, and what we have is, so 0.015 multiplied by 1100 seconds, that's 16.5, and charge is measured in coulombs. Okay, so 16.5 coulombs. The next question, question 11. A torch bulb, when it lights normally, allows 0.015 amps of current through it and has a potential difference of 6 volts. We're extending the same question. Now what we want to do is work out the energy delivered to the torch bulb in the 1100 seconds. So let me write down all the information we've got. So we've got the current at 0.015 amps. We've got the potential difference of 6 volts, but we also have the time that we are looking for the amount of charge to go through this torch bulb, which is 1100 seconds. Okay, now we want to work out energy. Okay, so how much energy or work done? So sometimes we use the letter W as well. Okay, so the amount of work done. Do we know a formula that connects these that has energy in it? We looked earlier and we did have that formula there, and that is energy. So voltage is equal to the energy over the charge. And what we are going to do is we're going to put that into a rearranging triangle. So that could have been work done as well. We could just replace it with W, but same thing. And that's what we have here. And we want to work out the energy. So the energy is equal, the amount of energy transferred in 1100 seconds is equal to the voltage multiplied by the charge. So do we have the voltage? Yep. Do we have the charge? Well, it's the exact same question as the previous one. So we have worked out the charge here. So that was 16.5 coulombs. So we did need to use another formula to work out charge. And that was the previous question. And if you look, that question and this question are the same numbers. So we've worked that charge out already. And that is 6 volts. And let me just move that. That's 6 volt multiplied by the charge, which was 16.5 coulombs. And the amount of energy transferred in 1100 seconds is the potential difference of 6 volt multiplied by 16.5 coulombs. So multiplied by 6 equals 99 joules of energy is transferred in that much time through that torch bulb. Okay. So the next question: as the length of the wire increases, what happens? So as the length of the wire increases, the longer and longer a wire gets, where are we? There are more electrons that are moving between the length of the entire wire. So there's going to be more collisions that the electrons will undergo when the electrons move from this side to this side, and they will have a larger resistance overall as they pass through that particular wire. Okay, so what we've got is the longer the wire, and this is what you would have done as an experiment as well, the resistance of the wire increases.